All right. So now we'll move over to section 2 of that same question 2021-2022 fluid mechanics past question. The figure below shows a continuous jet of water coming out from a pipe. It follows a trajectory profile as it travels in air from height z1 to z2 from initial velocity u1 to u2. If the weight of the jet is large enough to neglect the head loss due to friction, derive an expression for the vertical distance traveled. Okay, so this is the diagram as can be seen. All right, so this is a jet, okay, or water flowing through a jet of a pipe from um, initial velocity u1 to a final velocity u2, and of course the height at this point is z1 and the height at this point is z2. All right, so the equation is saying if this jet, the weight of the jet is so large such that the head loss due to friction is negligible, we are asked to derive an expression to show the distance or the height, sorry, to show the height of this fluid in this trajectory or in this profile. All right, so to do that, it's important for you to know that this fluid is at a certain height z1 and at a certain speed u1. Now, before takeoff, the speed is at rest, and the energy to which a fluid is at rest is called the potential energy. Now, when it takes off with its speed, it exhibits or gains kinetic energy. So, which means at this position, the total energy at that position is the potential energy plus the kinetic energy. So let's call this E1. Total energy at this position is the potential energy and the kinetic energy. Why? Why? The potential energy is the energy to which the fluid is at rest at this jet initially. Then when it gains this speed, it now flows, then gains kinetic energy. So which means total energy in state 1 becomes potential energy and kinetic energy. Same thing happens at state 2. When it comes to state 2, it moves with this speed and transforms to speed u2, which means it also exhibits kinetic energy. When it finally comes to rest at this point, at this height z1, it also exhibits potential energy. Therefore, the total energy here, let's call that energy E2. Total energy there is also potential energy plus kinetic energy. Okay, total energy at this point is also potential energy and kinetic energy. Now, what are these potential energy and kinetic energy? All right. Now, potential energy at the initial, or call that initial potential energy, okay, simply PE for potential energy is equal to the mass of the fluid times the acceleration due to gravity, because this fluid is suspended at a height. So mass times G times Z1. Z1 indicates the position, which is indicated here as Z1. Okay, that's the position. All right. The initial kinetic energy is also given as half 1 all over 2 u1 all squared, where u1 stands for the velocity of the flow. All right, so as indicated there, this is the speed of flow u1. All right, so in this position I said total energy becomes sum of kinetic energy and potential energy. Therefore, total energy at inlet, or total inlet or initial energy, we call that E1 is equal to the potential energy plus the kinetic energy. So E1 is equal to, what is our potential energy now? Potential energy gave us mgz1 plus kinetic energy is 1 all over 2 mu1 squared. So you call this equation 1. So same thing happens at the outlet or at the final stage. We also have potential energy and kinetic energy. So we now consider potential energy at the outlet, or outlet potential energy, or you can simply say final potential energy. P stands for potential energy, is equal to also mg, now is going to be z2, which is the height at that given position z2, okay, plus, okay, sorry. Next is final kinetic energy, and that's also going to be half 1 all over 2 m u2 squared, where u2 becomes its final speed as indicated from the profile. All right, so if you know this, therefore total final energy, which is E2, is now equal to, we said it's also going to be potential energy plus kinetic energy. So E2 is equal to potential energy at the final stage or at the outlet gave us mgz2 plus kinetic energy gave us 1 all over 2 mu2 all squared. Call this equation 2. Now, since the weight of the trajectory is so large that head loss due to friction is neglected, therefore this becomes the only two energies that we have. Now, at equilibrium, the both energies are equal. At equilibrium, equation 1 equals equation 2. So this simply implies that E1 is equal to E2. Initial energy equals final energy. And what was our initial energy? We had mgz1 plus 1 all over 2 mu1 squared to now be equal to final energy mgz2 plus 1 all over 2 mu2 squared. Now the question is asking us to find the height, derive an equation for the vertical distance. So we have to find the vertical distance, and that vertical distance is simply what? Z. We have Z1 and then we have Z2. So which means we need to make the Z's or the Z's subject of the formula per se. All right, so we need to make the Z's subject of the formula. So what I will do is this. I will simply send mgz1 over to this side of the equation. If I'm moving this, that means on this side of the equation, I'm left with 1 all over 2 mu1 squared. So this simply implies 1 all over 2 mu1 squared is now equal to, on this side, I have mgz2. So I'm sending plus mgz1 over here, positive sign, cross and equal to sign becomes negative. So I have minus mgz1. So I'm left here with plus 1 all over 2 mu2 all squared. Now, just like I've done for Z, let me send this kinetic energy over here. So bringing all kinetic energy together and keeping all potential energy together. So if I'm sending this over here, here I have 1 all over 2 mu1 squared. If I'm sending plus 1 over 2 mu2 squared over here, positive sign, cross and equal to sign becomes negative. So I have minus 1 all over 2 mu2 all squared. And that's going to be equal to, remember here I have mgz2 minus mgz1, which is these two left here now. All right, so I can factor, of course, something is common, 1 over 2, and mass is common here, so I can factor 1 all over 2 mass into u1 squared minus u2 squared. Of course, this is common. If I expand this bracket, I will still achieve this. So this is equal to, same thing happens here, mass and gravity is common between the two, so factor mass mg into, this becomes z2 minus z1. So from here I can actually make this becomes now my height. Z2 minus Z1 becomes the height which I'm asked to, okay, derive an expression from. So all I need to do is divide both sides by what? Mass and gravity. If I do that, I'm going to have 1, or you can simply say m into u1 squared minus u2 squared all over 2. Now, if I'm dividing by mg, this becomes mg, and that's equal to mg into z2 minus z1 all over mg. So I divided both sides by mg. Mg cancels mg over here. Mass cancels mass over here. So this simply implies that u1 squared minus u2 squared all over 2g is equal to what? Z2 minus z1, which is what we're asked to derive. So in essence, this is what we're asked to derive. So in essence, I can simply say this implies that z2 minus z1 is equal to u1 squared minus u2 squared all over 2g, and that is the derivation proved. So that's the answer to that particular question. All right, so that is question 3A in section 2. The very first question in section 2, the A part. Now the B part of that question also has a B part. The B part says, what is the velocity, discharge, and mass flow rate of water flowing out of a 32 centimeter diameter pipe at the base of a reservoir when the surface is at 45,000 millimeter? So let's pick out these parameters given to us. First of all, we're asked to determine the velocity, the discharge, and the mass flow rate, okay, of water flowing out of a 32 centimeter diameter. So diameter, okay, mind you, this is the B part, that's question 3B, okay. We're given diameter D to be 32 centimeters. So all we need to do is convert this diameter to meters. So we simply divide 32 by 100 and that will give us 0.32 in meters. So that becomes the diameter. All right, so they said the reservoir is at the base, okay, which has a surface at 45,000 millimeters. So that now this surface at 45,000 millimeter indicates the height of the reservoir. Please mind you, this surface at 45,000 millimeter indicates the height of the reservoir. So they are simply telling you that the reservoir's height or the surface of the reservoir is at a height of 45,000. All right, so this height is indicated as Z and is equal to 45,000 millimeters. So of course you have to convert this to meters by dividing through by 1000, and if you do that, you're going to have 45,000 divided 1000. That will give us 45 in meters. So it means that the height of the reservoir is 45 in meters. Now we're asked to find first velocity, and this question quite connects, okay, to the previous the derivation we just did. It quite connects, so you have to be very careful to actually observe that it actually connects. So look at the derivation we did. We had, okay, so we had that z1 minus z2. This z1 minus z2 indicates the vertical height or the position of that reservoir, and that's equal to u1 minus u2. u1 minus u2, u1 squared minus u2 squared indicates the velocity of that reservoir all over 2g. So which simply means that this is the equation we are going to use to solve that problem, where z1 minus z2 can stand for z. So we can ultimately say, or alternatively say, z1 minus z2 can stand for z, and that's equal to u1 squared minus u2 squared can simply stand for what? U all squared all over 2g. So we simply use this relationship to tackle this problem. So you have to be very careful. We are now condensing this whole equation into this. It's as simple as this. Z1 minus Z2 becomes Z. U1 squared minus U2 squared becomes what? U. Alright, all over 2G. So that's the equation we're going to use to tackle that problem. Alright, so from Z1, okay, from Z equals U squared all over 2G, we can simply make U squared subject, where U becomes the velocity. Alright, U squared subject, and it becomes 2G times Z by cross multiplying. We simply have 2G Z for U squared. Alright, for U squared. So from here you can simply make U subject, U is now the square root of what? 2G Z. That becomes the velocity. That's how we find the velocity, taking the root of what? 2 times gravity times the height. So this simply implies that U is equal to the square root of 2 times gravity remains 9.81. The height in this case now we've obtained is 45. Alright, so that's equal to the square root of, let's multiply everything together. 2 times 45 times 9.81, that gives us 882.9. So we have square root of 882.9. So if we take the square root of 882.9, we obtain 29.71 meters per second. So the velocity becomes 29.71. Alright, so this simply implies that u is equal to 29.71 meters per second. That becomes the speed of flow or the velocity of that fluid. The next question says find the discharge. Okay, we have to find discharge, and we know, okay, I says discharge, and we know that discharge Q is simply area times velocity. So we know the velocity. All we need to do is compute the area. We are given diameter to be equal to 0.32 in meters. So if we have diameter to be 0.32 in meters, then we can find area. Area is pi diameter squared all over 4, and that's equal to pi remains 3.142 multiplied diameter is 0.32 all squared all over 4. So I'll compute everything together to save time. So this implies that area will be equal to, so we have the area to be 0.080 in meters squared. So this gives us the area. Now if we've obtained the area, we can simply find discharge. Therefore discharge Q is equal to, area is 0.0804352 multiplied by speed. Speed is 29.71. This implies that discharge is equal to, okay, multiply by 29.71. So we have 2.39. Discharge equals 2.39 meter cube per second. So that becomes the discharge of the fluid through the pipe. Alright, so the final question says calculate the mass flow rate. Okay, so we have to find the mass flow rate of water flowing through the pipe. Okay, final question says calculate the mass flow rate. Alright, so mass flow rates, I've already given this when we did some videos on test preparation of fluid mechanics for all Rivers State University students, and I said mass flow rate m dot can be given as density times discharge. Now since we're talking about water, it means density becomes density of water, which is constant 1000, and that implies that mass flow rate is equal to density of water is 1000 multiplied by the discharge gives us 2.39, and this is obviously 2390 kilograms per second. That becomes the mass flow rate of that fluid. Alright, so that's it on question 3. That's section 2. Very first question 3 and question 3A and question 3B on section 2. So we'll move next now to still on section 2, question 4A and question 4B. So let's still on section 2, now question 4A, which is the first question, which is the second question in section 2. So question 4A says, in figure 3 below, if pipe 1 has diameter 6 mm and mean velocity 3 meters per second, pipe 2 with a diameter 50 mm takes 40% of the discharge, while pipe 3 has diameter 7 mm. What are the values of discharge and mean velocity in each pipe under a steady and incompressible flow condition? So we are given the pipe, as can be seen. Okay, this is the pipe. So we are given that pipe 1 has a diameter of 6 mm. So diameter of this pipe is pipe 1, this is pipe 2, and this is pipe 3. So let's get out the given parameters. So diameter of pipe 1, okay, this is question 4A, given diameter of pipe 1, call that D1 is given as 6 mm. So converting this to meters, that becomes 6 by 10 to the power of minus 3 a meter. Simply dividing 6 by 1000, that gives you the diameter of pipe 1. Okay, and also it has a velocity, a mean velocity of 3 meters per second. So velocity of pipe 1, call that V1, was given as 3 meters per second. Velocity of pipe 1 was given as 3 meters per second. Now the next question says um, pipe 2 has diameter 50 millimeter. So diameter of pipe 2, call that D2. Okay, diameter of pipe 2, call it D2. D2 is actually 50 millimeter. Converting this to meter, divide by 1000. That will give us about 0.05 in meters. And the condition says pipe 2 takes 40% of the discharge. Alright, so pipe 2 takes 40% of the discharge. So discharge in pipe 2, call that Q2, is actually 40% of Q. 40% simply means 40 divided by 100. So you have 40Q all over 100. This simply means that discharge in pipe 2 is actually 0.4 Q. Pipe 2 takes 40% of the discharge. Next, we are given that pipe 3 has a diameter of 7 millimeter. So D3 equals 7 millimeter, which is also 7 by 10 to the power of minus 3 in meters. That's the diameter of pipe 3. Now, the question is asking us to determine the velocity in each pipe and also the discharge through the pipe. Okay, what are the values of discharges and mean velocity in each pipe? All right, so that's the question. All right, so for the first pipe, diameter 1 was given to us as 6 millimeter, which is 6 by 10 to the power of minus 3, and we're given velocity as well, which means we can find the discharge of pipe 1. All right, so discharge of pipe 1 equal, that's Q1, call that Q1, and that's equal to the area of pipe 1 multiplied by the velocity of pipe 1. It's as simple as this. So all we need to do is find the area, where area of pipe 1 becomes pi diameter 1 all squared all over 4, and that's equal to 3.142. That's for pi multiplied by diameter 1 being the first diameter, or diameter of the first pipe, is given as 6 by 10 to the power of minus 3 all squared all over 4. So I'm going to do all of this together to obtain the value of the area A1 to be equal to 3.142 multiplies 6 by 10 to the power of minus 3 squared divides by 4. So we have A1 to be 2.8278. 2.8278 multiplied by 10 to the power of minus 5 in meter squared. This becomes the area of pipe 1. So if you know this are the area of pipe 1, therefore discharge of pipe 1, we said is what? Area times velocity of pipe 1. Okay, area times V1. Okay, so the area is 2.8278 by 10 to the power of minus 5 multiplied by speed 1. Speed 1 was given in the equation as 3 meters per second, so multiply by 3. This gives us the discharge of pipe 1. So multiply by 3, we have 8.48, 8.48 approximately, multiplied by 10 to the power of minus 5 meter cube per second. This is the discharge in the first pipe. Now, I've made a video on discharge earlier in my fluid mechanics series. You can do well to watch it up for proper understanding. And I think I've solved something similar to this as well. The discharge through this pipe is called Q1. We found this. Discharge through this pipe is called Q2. We've also, and discharge through this pipe is called Q3. Okay. Now, this pipe Q1 is what is actually discharging into Q2 and Q3. So Q1 becomes the host. Okay, it becomes the host or the source. Therefore, and it is still Q1 that branches into Q2 and Q3. This simply means that the discharge Q1 is equal to Q2 plus Q3, because it is Q1 that gave birth to what? Q2 and Q3. The whole supply is coming from Q1. Therefore, Q1 equals what? Q2 plus Q3. I know Q1. All I need to do now is what? Find either Q2 and then Q3. But Q1 becomes discharge through the whole system. Q1 becomes equal to Q2 plus Q3. All right. So if Q1 is the source, that supplies the other discharges, and the condition told us that Q2 takes 40% of the discharge, whereas the discharge itself is Q1, that is the source supplying the entire section with the fluid. Therefore, it means that from the condition Q2, okay, this implies this Q2 is equal to 0.4 of what Q1, because Q1 is the source, that's the source pipe that supplies the fluid to all the other that supplies the fluid to all the other pipes. So it means Q2 becomes 0.4 Q1, because from the condition it was stated that Q2 has 40% of the discharge and the discharge is Q1, okay, which we found here Q1 is this. This implies now that Q2 becomes 0.4 times what Q1. Remember 40%, so you divide 40 by 100, you have 0.4. Q1 gave us 8.48 by 10 to the power of minus 5. So this simply means that Q2 itself is equal to, okay, times 0.4, that gives us 3.39. Q2 equals 3.39 multiplied by 10 to the power of minus 5 meter cube per second. So this is second discharge, this is the first discharge. Alright, so if you know these two now, we can now simply employ this equation Q1 equals Q2 plus Q3 to find what the third discharge. Okay, alright, so from Q1 equals Q2 plus Q3, this simply implies you can make Q3 subject now. Q3 becomes Q1 minus Q2. Q2 comes here now, becomes Q1 minus Q2 for the third discharge. And this implies that Q3 is equal to Q1 give us 8.48 by 10 to the power of minus 5 minus Q3 itself now give us 3.39 by 10 to the power of minus 5. So this implies that the third discharge Q3 is now equal to 8.48 exponential minus 5 minus 3.39 exponential minus 5. That gives us 5.09. Okay, Q3 equals 5.09 by 10 to the power of minus 5 meter cube per second. So that becomes the three discharges through the pipe. So if you want to confirm, you can go ahead and test if Q1 will be equal to Q2 plus Q3, knowing that Q2 is this, sorry, Q3 is this, and then Q2 is this. Add them together and see if you're going to obtain the first discharge, just to confirm that that answer is correct. Okay, so if you know the discharges now, the next question, so we should also find the mean velocity of each pipe. So we need to find their velocity. So velocity of pipe 1 was already given in the equation as 3 meters per second. All we need to do now is find velocity of pipe 2 and that of pipe 3. Now recall, okay, for pipe 2 we can obtain that Q2 is equal to A2 times V2. So which means to find the velocity of pipe 2, we simply divide. V2 becomes discharge 2 all over area 2. And this is equal to discharge in pipe 2 gave us 3.39. So Q2 gave us 3.39 by 10 to the power of minus 5 all over area. Of course, we know that area is equal to pi diameter squared all over 4. So diameter in this case becomes diameter of pipe 2. Okay, so this becomes pi is 3.142 times diameter of pipe 2. Pipe 2 has a diameter of 50 millimeter from the condition given. Diameter of pipe 2 D2 was 50 millimeter, which gave us 0.05. Okay, so we simply put there 0.05 all squared divided by 4. Okay, so this will give us 3.39 by 10 to the power of minus 5 all over. So I'm going to compute this area at once, okay, just to save time. So I have 0.05 all squared multiplies 3.142 divided by 4. That gave me 1.96375 by 10 to the power of minus 3. 1.96375 by 10 to the power of minus 3. So I'm going to divide these two now. 3.39 by 10 to the power of minus 5 divides 1.96375 by 10 to the power of minus 3. That will give me the velocity of pipe 2. Okay, so 3.39 exponential minus 3 minus 5 divided by answer. So that gives me 0.017 meters per second. Okay, so velocity of pipe 2, this implies that V2 is equals 0.017 meters per second. That becomes V2. Alright, so to find V3, we'll use the same relationship for velocity. V3 becomes discharge 3 all over area 3. And that's equal to discharge 3 gave us 5.09 by 10 to the power of minus 5. Discharge 3 gave us 5.09 by 10 to the power of minus 5 all over, once again, A3. Of course, area is pi d3 all squared all over 4. So this is formula to calculate area. D3 now becomes the diameter of pipe 3. So pi remains 3.142 times diameter of pipe 3. Not forgetting, diameter of pipe 3 was given to us as 7 millimeter. Over here, you have 7 millimeter, which is 7 by 10 to the power of minus 3. So you simply append that there. In place of diameter, you have 7 by 10 to the power of minus 3. Remember, all squared because it is squared, all divided by 4. So this will be equal to, put down your discharge, 5.09 by 10 to the power of minus 5 all over. So I'm going to compute the area just as usual, calculate all at once. So I have 7 exponential minus 3 all squared multiplies 3.142 divided by 4. That will give me 3.849 or 84895. 3.84895 by 10 to the power of minus 5. Okay, so I have this. Alright, so all I need to do now is divide. This simply implies that V3 is now equal to, so divide that answer by with 5.09 by 10 to the power of minus 3. So 5.09 exponential minus 5, please. Divide by answer. Okay, that gives us the speed as 1.3. We have 1.3 meters per second. So notice that V1 has a speed of 3 meters per second. V2 has a speed of 0.017 meters per second. And V3 has a speed of 1.3 meters per second. And you might want to know, or why is it so? It is simple. The larger the diameter, the smaller the speed of flow. So if the diameter is large, the speed becomes smaller. For instance, the diameter of pipe 1 from the question was given to us as what? 6 millimeter. Diameter of pipe 1 was given to us as 6 millimeter, and the speed was 3 meters per second. So it has the highest speed because its diameter is small compared to diameter of pipe 2. Pipe 2 has 50 millimeter. Pipe 2 has 50 millimeter, which is larger than 6 millimeter. Pipe 3 has 7 millimeter, which is also larger than 6 millimeter. But nothing between pipe 2 and pipe 3. Pipe 3 diameter is smaller than what? That of pipe 2, which is why pipe 2 is having the least velocity compared to what? The other two diameters. So as can be seen here, V1 is 3, V2 remains 0.017, and then V3 remains 1.3. So that is it for the second part of that section or that particular question. Okay, so that's question 2a, question 4a, which is the second part of section 2. So let's now calculate for question 4b. So still on section 2, question 4b, I will continue the solution here. Question 4b, I'll continue the solution there. Question 4b on section 2. Question 4b says, what minimum diameter of pipe is necessary to carry 0.03 kilogram per second of air with a maximum velocity of 6 meters per second, temperature of 27 degrees Celsius, and absolute pressure of 2.5 bar. Take R, which is specific gas constant, to be 287.8 joules per kilogram per Kelvin. Alright. So we are asked to find what minimum diameter. Diameter is unknown. Diameter is unknown. D is unknown. Okay, is required to carry 0.03 kilogram per second. So when you see kilogram per second, it is simply telling you the mass flow rate. So mass flow rate, which is m dot, was given as 0.03 kilograms per second. Okay, of air with a minimum velocity, with a maximum velocity of 6 meters per second. So we are given velocity at 6 meters per second. We are given velocity v to be equal to 6 meters per second. We're also given temperature of 27 degrees Celsius. Okay, temperature T was given as 27 degrees Celsius. So we convert this to Kelvin, becomes 27 plus 273, just to convert it to Kelvin. Alright, so this implies that temperature is equal to 300 Kelvin. So we have the temperature to be 300 Kelvin, and the pressure was given as 2.5 bar. So we have pressure P equals 2.5 bar. We also convert this to Pascal, and 1 Pascal is 101325 Pascal. Okay, so this will give us pressure as 2.5 multiplies 101325 in Pascal. Okay, so this implies that pressure is equal to, so multiply 2.5 by 101325 Pascal. 325 multiplies 2.5, so we have the pressure to be 253312. 253312.25, okay, 0.5 Pascal. So this becomes the value of the pressure in Pascal, and we are asked to find the diameter. Okay, diameter of the pipe. Alright, so we're asked to find diameter. Diameter is unknown. We're also given gas constant R to be 287.8 joules per kilograms Kelvin. Okay, we're given gas constant to be this, and we're asked to find the diameter. Now, first thing that comes into your mind is, how do you find diameter? Okay, and we know that whenever we are talking about flow in fluid or fluid flow through pipe, the first thing that comes to our mind should be discharge always. And if discharge is area times velocity, it means we can find area, and diameter always lies in the area. But then what is the discharge? Recall from I gave us an equation earlier when we did videos on test preparation. I said that mass flow rate, okay, m dot, is actually density times discharge. So it means that we know the mass flow rate. All we need to do is to find the density of this fluid, then make the discharge, solve it on the formula. If we can find discharge, then velocity was given to us. It means we can find area. From there, we can find the diameter of the pipe. So our interest now is to find discharge. But then, how do we get density? Recall from ID gas, because the conditions that have been given to us now involves an ID gas. We're seeing an ID gas constant there, 287.8. So from ID gas, we have that PV is equal to mRT, where m is mass and V is volume. P remains pressure, T remains temperature, R remains gas constant. So notice that if I make mass all over volume subject, that is simply dividing through, okay, let me just do a rough sketch of it over here. I have that PV is equals mRT. If I divide through by volume, divide through by volume. Volume cancels volume from here. I'm left with only P on this side of the equation. So I have here that P is equal to what? It becomes M all over V times, I'm left with what? RT over here. So to make M over V subject, I have to divide both sides by what? RT. So this simply implies that P all over RT is equal to what? M divided by V. And M divided by V talks about mass all over volume. And we know that mass over volume stands for what? Density. So this simply implies that density of that fluid is simply what? Pressure all over RT. Okay, so that's how you find the density of that fluid. And this is equal to pressure. We've already found pressure in Pascal. I will have it to be 253,312.5 all over R stands for the gas constant, and R was given as 287.5 multiply temperature. We converted that to 300 Kelvin. Okay, so as usual, I will evaluate everything at once to obtain density. All right, so 287.5 multiplied by 300. Okay, that gives me 86250. So I'm going to be dividing that. I'm going to be dividing 2533.12.5 with that value. Okay, by answer. So that gives me 2.94. Okay, so we have 2.94 approximately for the density, 2.94 meter kilogram per meter cube. Okay, that's for the density. So I have my density now to be this. Hence, from the relationship mass flow rate equals density times discharge, it means I can make discharge subject of the formula. It becomes mass flow rate all over density. Making discharge subject, it becomes mass flow rate divided by density. So this is equal to, recall from the question, the mass flow rate was given to us as 0.03 kilogram per second, as can be seen here. So therefore this becomes 0.03 divided density, which is 2.39. Okay, so this implies that discharge is equal to 0.03 divides 2.39. So that gives us 0.01255, 0.01255 in meter cube per second. Okay, so this gives me my discharge. So if I have this to be the discharge, it means now I can find the value of the area. So if I have this to be the discharge, you recall that discharge Q simply means area times velocity. So which means I can make area subject, knowing that diameter lies in area, I can make area subject, it becomes discharge all over velocity. So this is now equal to my value of discharge. I obtain the value of discharge to be 0.01255. So I have 0.01255 all over the velocity from the question. Okay, from the question, velocity was given to us as 6 meters per second, as can be seen here. Alright, so divide by 6, that gives me the area. Therefore, area A is equal to, so we divide that value by 6. We have 2.092 by 10 to the power of minus 8. 2.092 by 10 to the power of minus 8 meter squared approximately. So it becomes our area. Now, if this is our area, recall that area is pi diameter squared all over 4. So if I cross multiply here, 4 multiplies A, that will give me that 4A is equal to pi diameter squared. And therefore, I can make diameter squared subject here by dividing through by pi. I have that D squared is equal to 4A all over pi. Hence, to find diameter, this implies that diameter D becomes the square root of 4A all over pi, and that's equal to square root of 4 times A gave me 2.092 by 10 to the power of minus 8 all over pi is 3.142. So D is equal to the square root of, so I'm going to evaluate everything including the division. So I have answer multiplied by 4 divides 3.142. Okay, that gives me 2.663. 33 by 10 to the power of minus 3. Alright. So all I will need to do at this point is take the square root, and therefore D is equal to taking the square root of that answer. Okay, that gives me 0.052. I have 0.052 in meter, so this becomes the minimum diameter necessary. Alright, so that becomes the answer to that particular question. So that's it on section 2, question 3 and question 4. So I will see you in the final section, that's section 3, talking about question 5 and question 6. Thanks.